Alright, in this video, we're going to be talking about how to actually calculate surface properties from the doublet strengths that you calculated last time. So, we've gone through all of this, we've got our geometry, we've got it processed, we calculated influence coefficients, we figured out what our doublet strength distribution is, and that's great. Problem is, the doublet strength distribution doesn't really tell us anything directly. We'd like to know what our surface pressures are, what our loads are, that kind of thing. And so we need to be able to get from this doublet distribution to surface velocities, and then that'll give us surface pressures, which gives us forces and loads. Okay? So let's work on that. Now, in order to get to being able to figure out what our velocities actually are, we need to review some of the theory here. So, if you remember, we said that mu, our doublet strength, is equal to the jump in velocity potential across the panel. Okay? This is really fundamental. Please remember this. If I've not iterated enough times, remember it now. We should also recognize with this, if we look at the jump in total potential from going from the inside to the outside, so say we go phi minus capital Phi inner, well, that's just phi infinity plus our exterior perturbation potential minus phi infinity plus our internal perturbation potential. Okay? And these phi infinity doesn't change. Phi infinity is ignorant of where the configuration is. And so these two terms cancel each other out. And this is equal to phi minus phi inner, which is equal to mu. Okay? So this is an important thing to remember, that mu is not only equal to the jump in perturbation potential, but also the jump in total potential. Okay? And that's useful for what we're about to discuss. So, if you remember from when we talked about why is the Neumann system singular, I explained, and I asked you to take this on faith, that if I have a body, and on that body I enforce the zero normal flow boundary condition, so I say v dot n is equal to 0, I can show that our velocity potential inside here is equal to some constant. Okay? And I should be very explicit. This is the total potential inside the configuration. Okay? Because we're dealing with the total velocity here, and we've said that v dot n is equal to 0 everywhere on the surface, because of that we know the total potential on the inside is equal to some constant. Okay? Now if I want to look at the velocity on the surface, so v just on the surface and just on the outside of this configuration, well, that's just equal to the gradient of the total potential on the surface, right? Now, if you remember what we said just before, doublet strength represents a jump in velocity potential going from the inside to the outside. So I can now write this as Vs is equal to the gradient of our inner total potential plus mu, because mu is our jump. And remember we said mu is the jump either in perturbation potential or in total potential. It doesn't matter here. Okay, so we've got this for our surface velocity calculation. And again, we're only looking just at the surface. You know, if you wanted velocities off of the body, somewhere out in the free stream, or somewhere out in the flow, this equation doesn't work. But since we're just looking just at the upper surface of the configuration, we can use this equation. And we can use it to great advantage because the gradient operator is linear. We can distribute it through. we can distribute it through onto both terms. And remember, we said phi sub I is equal to a constant. What is the gradient of a constant? Well, that's just 0. So that term goes away, and we're left with V on the surface is equal to the gradient of mu, which is pretty slick. This tells us that in order to calculate surface velocities, we don't need to recalculate influence coefficients. We don't need to sum up induced velocities anymore. All we need to know is the gradient of doublet strength, local to where we're looking at the velocity. Pretty cool. So, how do we get that? Because again, we've gone ahead and said that our doublet strengths are constant. So, with our discrete approximation to the problem, if this is our true doublet strength across the surface, then we have the approximation that looks like that. And everywhere here, grad mu is 0, because on each panel mu is constant, and we take the gradient of that, it's not going to get us anywhere. But we need to remember this is just an approximation, okay? So what we can do is we can say, well, I know this is an approximation, so what if I take and over this panel, I use its neighbor information, I use the information on its neighbors to fit a line through that. And then from that line I can calculate grad mu, because now I've got a linear distribution and it'll actually give me something. Okay, so that's what we're going to do. The way we're going to do that is we're going to look at the panel, and we're going to say that we're looking at, let's say we're looking at panel 1. And panel 1 has neighbors 2, 5, and 6. And we know where the centroid of each of these is. Now remember, and this is very important for what we're about to do, we've said that the local coordinate frame has its origin at the centroid of this panel. So x prime and y prime are centered at the origin of panel 1. Okay? And we're going to say that we're going to approximate our doublet strength as being linear in the regions surrounding this panel, for panel 1. Now to do that, we have the relationship that mu as a function of x prime and y prime, so again we're looking at mu on the panel anywhere, is going to be some mu naught plus mu x, our x derivative term, x prime, times x prime plus mu y prime, y prime. Okay, so this is all in the local frame. And now this mu naught term represents our constant, and mu sub x prime and mu sub y prime, those are our derivatives of doublet strength in the x and y prime directions. So we've got this really simple equation that describes for us our distribution across the panel. And again, it's linear. It's, well, in 2 dimensions we're linear. Okay. Now x prime and y prime are 0 at the centroid. And we're going to say, well, we've satisfied boundary conditions at the centroid of our panels. I'm going to say that for each given panel, mu naught is equal to just the doublet strength on that panel. So in our case, this is going to be mu 1. If we were looking at panel 12, this would be mu 12. If we were looking at panel 252, this would be mu 252. So we get the relationship. We can bring this over to the other side. We can say that mu at some point in local coordinates minus mu 1 is equal to mu x prime plus mu y prime. Now what we want to get out of this is we want to figure out what mu x prime and mu y prime are. Because if we can do that, then we know that the gradient of mu in the local coordinates is equal to mu x prime mu y prime, and then 0. We're going to assume that there's no vertical variation in mu here, which, again, we've said v dot n is 0, which says that the normal derivative of doublet strength with respect, or the normal derivative of doublet strength in the normal direction is 0. So this just kind of comes out of our boundary conditions we've applied. Okay? So that's why we're formulating this equation. We're looking to figure out what are mu x and mu y. Well, we don't know those, but since we've solved for our doublet distribution, we do know what mu1 is. We also know mu at a few other points, namely at the centroids of the neighboring panels. So since we've solved for our doublet strengths anywhere, I know what mu is at the centroid of panel 2. I know what the centroid mu is at the centroid of panel 5, and I know what it is at the centroid of panel 6. So I can take and I can write this equation down here a few different times for these centroid locations. And I can say, for example, well, I'll write all of them out. Mu on panel 2 minus mu on panel 1 should be equal to mu x prime times x prime of at 2. So this is the local scaled, the local coordinate of the centroid of panel 2 with respect to panel 1. We'll get to exactly what that is in a second. Mu y prime 2. Okay, and the same thing for the other panels. So mu on the centroid of panel 5 minus mu 1 should be equal to mu x prime x5 prime plus mu y prime, sorry, not x5, y5 prime. Okay, and then the same thing on panel 6. So now we get 3 equations for which we need to solve for these unknowns, which are the same between all the equations. So we can gather these up between those, and we can write out a matrix equation. If you're not yet bored of solving matrix equations, here's another one coming your way. This one's a little more interesting. And when we write that out, what we get is, we get x2, we get our x and y coordinates of our neighboring panel centroids gathered into this left-hand side matrix. And that's multiplied by our derivative terms, so mu x prime, mu y prime is equal to mu 2 minus mu 1, mu 5 minus mu 1, mu 6 minus mu 1. Now, the astute among you will say, well, hold on a second. 3 equations, 2 unknowns, this is overdetermined. And you're right. So what we need to say is this is approximately equal. So we're not going to find a mu x and a mu y that exactly satisfy this relationship, but we can find ones that are pretty good, that'll approximately give us this. And we do that using least squares approximation. Now you can solve that just by saying, okay, this is my A matrix, this is my B vector, and plugging that into numpy.linalg.least squares. You can do that. That's fine. You're also welcome to calculate the least squares solution directly, which I'll show you what that is if I give myself a little more room here. So notice we can't invert A because A isn't square. But if I take and multiply both sides by A transpose, and this is a very this is a very lazy explanation of least squares, and not at all justified. If you'd like to look into how exactly least squares works, some numerical methods textbooks touch on it. The one I learned it from is Mathematical Methods and Algorithms for Signal Processing by Moon and Sterling. I recommend that one. It's deep, but it's good. Anyway, if I take and multiply both sides by A transpose A times, I'll just call this vector x for now, plus A transpose B. Well, A transpose is a 2 by 3 matrix. And if we take a 2 by 3 by 3 by 2, that ends up being 2 by 2. And then multiplying a 2 by 3 matrix by a 3-element vector, that'll give us 2 elements over here. So now we have a 2 by 2 matrix times a 2-element vector is equal to a 2-element vector. And that's a totally valid system of equations. We can solve that directly using matrix inversion, and we get x is equal to A transpose A inverse A transpose B. Now I know all of you are saying, hey, you told us never, ever, 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 ever invert a matrix explicitly, and I did say that. This is one of those exceptions, and I'll say why. This is a 2 by 2 matrix, so the number of operations it takes to invert this matrix is really, really, really small. You know, you're doing probably no more than 10 multiplications and additions. Okay. Were you to invert your system matrix for solving for your doublet strengths, that's lots and lots and lots and lots and lots of operations and numerically stable, unstable calculations. So normally we don't calculate the matrix inverse because you just get garbage out. But this is such a minor computation, again, just inverting a 2 by 2 matrix, that it's not a big issue, and you're welcome to do it explicitly. Now in your code, do whatever you like. You can use numpy.least squares, or you can calculate it directly using this method. I'm fine either way. Feel free to implement both and see if there's any differences. See if one's more efficient than the other. I'm sure you'll see some time savings with one or the other. Don't ask me which, but yeah, feel free to check that out and see how it works. Okay, so once you get that, this x vector that you get out of your solution will be this right here. And you can take and plug that into a vector, again, where we say our gradient in the local frame of mu is equal to mu x prime, mu y prime, and 0, where these we calculated from our least squares. And then to get the gradient of the doublet strength in the global frame, all we have to do is multiply that by A, L to G, and that'll transform it right back for us. Pretty slick, right? So that's all there is to that. I did say that I would explain how to get the neighboring centroid locations in local coordinates. Well, like we talked about in a previous video, if you've got some point that you want in local coordinates, so P prime, that's just equal to A G to L times P in global coordinates minus P centroid, where P centroid is the center of the panel you're looking at. Remember, we choose the origin of our panel to be the centroid. So this is what you use to calculate the local coordinates of the neighboring panel centroids. Once you've got those, you plug them into your matrix equation here. If I can get rid of the black boxes of death. And then doing that, you can run through all this, you can solve it, you get out your gradient of your doublet strength in local coordinates, transform that to global coordinates, and that will be your velocity. Okay, we're going to assume that velocity is constant over each panel, so you're going to loop through each panel. For each panel, assemble this least squares system, solve it, and use that to calculate the velocity. Okay, that's all for this video. In the next one, we'll talk about how do we use then surface velocities to calculate pressures and forces. And I'll see you in the next one.